go ahead.
Okay, thanks. Thanks for the introduction. And hello, everyone. I'm Qing from Tsinghua University. And today I will show our work, a 28 nanometers, 83.23 teraflops per watt POSIT-based computing memory macro for high accuracy AI applications. And first, I'm sorry that the first author, Professor Wang, he is on an unexpected business trip and is unable to join us today, so I will be stepping in to deliver the presentation on his behalf. And today's presentation contains these 5 parts. And first, I will introduce the background and motivation. So we can see that in recent years, the AI technology has become an important part of our daily lives, covering huge a variety of applications like the AIGC and other scenarios. And as the AI technology continues to advance, current AI tasks are becoming increasingly complex. And these complex AI algorithms rely on exponentially growing model size, which leads to a significant increase in memory access power consumption. Additionally, high precision calculations are required here to ensure the application accuracy. So we can see that many researchers propose the FP computing memory, we call them FP-Sim. It has become a promising technology that addresses the memory war issue for AI applications while achieving high precision computation. But traditional floating point data format failed to simultaneously balance the data range and the data precision of the weights, activations, and gradients in AI training process. As shown in this figure, the traditional FP16 format with 5 bits of exponent allocates 10 bits for the mantissa to improve the data precision, but it fails to cover the entire data range. And the BF16 format with 8 bit for exponent and 7 bit for the mantissa, so it has a limited mantissa bit width, resulting in a precision loss. Of course, we can use something called 1-8-10 floating point data with higher bit width to satisfy both data range and the precision requirements, but it would lead to a significant increase in power consumption. So we found that the emerging POSIT data format exploiting dynamic bit widths that adapts to various data distributions can use a low bit width to achieve nearly the same training and inference accuracy as high floating point bit width does. The POSIT data consists of 4 parts: the sign, regime, called R, exponent, called E, and mantissa, called M. Please notice that the R and M, the bit widths, are dynamic, which allows a data range and the precision trade-off at runtime. And R here is a unary code with successive zeros and ones, like 11110 or 00001. The decimal value of R is a number of successive ones counts minus 1 for positive values, and the successive zeros count for negative values. So we can see that the POSIT computing requires the decoding of R to get the real POSIT value for computation. So with the dynamic data expression to adapt data distribution, the POSIT bit can use 8 bit to achieve comparable accuracy compared to BF16 or FP16 in our test with the VITB on image classification tasks. And this process, it only introduced 0.4% accuracy loss, but the POSIT 8-bit leads to 27% of the energy reduction. So it is a very promising data format. However, we found that it is challenging to design an energy-efficient POSIT-based SIM macro due to dynamic properties of the POSIT data format. The first challenge is the dynamic regime processing of POSIT. Different from direct exponent calculations of traditional floating point numbers, in the case of 2 POSIT data, the dynamic and changing regime needs to be extracted before performing the calculation. And it is then decoded into a decimal number for computation. And after the computation is completed, the decimal exponent needs to be re-encoded back to regime for storage. The additional dynamic extract and codec logic requires 2.62 times higher power than fixed exponent procession in conventional floating point in our tests. And the second challenge is about the dynamic bit width of mantissa of POSIT. The traditional floating point numbers have a fixed bit width for the mantissa of all the data, allowing us to pre-schedule the structure of SIM, which can efficiently accommodate the fixed mantissa width. However, in POSIT, the mantissa bit width of the POSIT is changing because of the regime, which clashes with the structured SIM architecture. Therefore, when we storage the POSIT data into a SIM macro designed to store weights with a fixed bit width, it will result in up to 41.3% of SIM underutilization. And the third challenge is a dynamic mantissa accumulation. For traditional floating point data, we align two mantissas, and there is typically an overlap that requires the use of wide width adders for computation. However, for the POSIT data format, it's a different story. It involves dynamic alignment for the mantissa with dynamic bit widths. This dual dynamic characteristics resulted in a 66.8% of dynamically aligned mantissas having no overlapped bits, where the 4 adders actually performs x plus 0 equals x, this simple operation. The original A plus B calculation with a power consumption of 174.38 nanowatts can be simply replaced with a OR logic, resulting in a power consumption of only 29.7 nanowatts. To address the above challenges, we proposed a POSIT-based SIM macro with 3 features that effectively handles the dynamic properties of the POSIT data. And this slide shows the overall architecture of the SIM macro that we propose. It consists of the BRPU here, 16 SIM cores with CPC SIM arrays, and 16 adder trees with the CASU. The BRPU here replaces the regime codec logic with shift and OR logic to save the regime preprocessing energy. The CPC SIM array exploits spare bits to perform dual-bit MAC to increase the SIM utilization. And the CASU here simplifies the addition logic to bitwise OR operation to reduce accumulation power. And I will detail into these modules in the next part. And first, I will show the bidirectional regime processing codec. Different from floating point data as we shown before, POSIT has an additional dynamic regime in addition to the exponent and mantissa. And this regime is crucial to POSIT for the data precision. As we talked about before, it uses successive count of ones and zeros for the decimal value. Therefore, in computation process of the 2 POSIT numbers, regime processing mainly involves 2 steps. Step 1 is the 2 decoders dynamically selecting the leading 1 or leading 0 detection based on the sign bit of the 2 POSIT data, and then obtaining the decimal representation of the regimes based on the count of consecutive zeros or ones. And in step 2, it adds the decoded decimal value of the 2 POSIT data, and then one encoder re-encodes the computed result into the output regime. Although the dynamic regime increases the adaptability of POSIT to different data distributions, the extra codec logic required for regime processing has increased power consumption overhead. Therefore, instead of decoding the regime into decimal numbers for computation and then encode them back, we proposed a BRPU that replaces this complicated codec addition process with simple shift and OR operation based on the characteristics of regime using the count of consecutive zeros and ones of the value. Taking the addition of 2 POSIT regimes as an example, their computation essentially involves increasing the count of consecutive ones, and therefore the BRPU only decodes the regime of 1 POSIT data, denoted as A here, into the decimal value RA to shift the regime of the other POSIT data. We call them B. So B is shifted by RA. And then it concatenates A's regime with B's shifted regime using a bitwise OR operation. This operation increases the count of ones in regime of data A on the regime of B, while eliminating the need for one regime decoder, resulting in a saving of 23.6% in area and 22.2% in power consumption. And BRPU contains a bidirectional shift mechanism to reduce shifting energy by decoding the smaller r while shifting the large R. As we can see, for RA equals 11110 and RB equals 110XX, the BRPU can reduce the shift code from 4 to 2, saving 50% of shifting energy. And when simulated with the TSMC 28 nanometer technology at 400 megahertz, this mechanism can reduce the average shifting power from 0.25 microvolts down to 0.15, resulting in a 14% of shifting energy reduction. In addition, for two regimes with a different size, directly shift and OR operation based on processing buffers, based on the registers, suffers from the shifting error. Specifically, once the shift step is larger than the regime bit width, it moves all the regimes away. So it introduces a shifting error. Of course, we can increase the bit width using an extra shift bit for overflow for the regime to avoid such shifting errors, but it would result in doubling of the shift area and more power consumption. So in our design, we can address this shifting error for two regimes with different size. Since it always decodes the smaller R to shift the larger R, and there is never an overflow problem, and thus the shifting errors are eliminated. Therefore, this mechanism avoids the need for longer shift logic and reduces the shifting error and power consumption overhead by about 50%. And the second feature is the crucial bit pre-compute and store SIM array, which improves the hardware utilization for dynamic Mantissa. With the variation of regimes, the Mantissa bit width of the POSIT data also changes. In a traditional FP format like FP16 or BF16 have all fixed Mantissa widths, allowing for the design of SRAM structures in advance to support the corresponding width format. But the dynamic Mantissa width of the POSIT cannot be determined in advance, which leads to SRAM cell waste for a specific structure of the SIM array. For example, during the training process of Resident 18, the 3-bit and 4-bit Mantissas have similar proportions. To accommodate the 4-bit Mantissa, the SRAM needs to be designed as a structure that holds 4 bits per data. And this 4-bit SRAM structure results in 2 bits or 1 bit of cell wastage when stored in the 2-bit or 3-bit data, which leads to a wastage rate as high as 48.9%. We proposed a critical bit pre-compute and store, we call them CBCS, this technique for the SIM array. It utilizes the spare bits to enable the SIM array to perform dual-bit MAC operation in one cycle. Specifically, during the widely used bit serial computing in the SIM array, it computes W0 times A00 plus A02 instead of W0 times A00 by leveraging the spare bits. As a result, it only takes 2 cycles to compute a 4-bit A, resulting in a throughput that is 2 times higher. Here is the overall architecture of the proposed CPCS SIM array. The SIM array consists of an 8 times 48 SIM array, a load controller, a critical bit computing unit, and a 3-to-8 decoder. The 48-bit cell of each row is separated into 12 SIM units. Each contains 4 SIM cells. The 4-bit SIM unit works with the above-mentioned 3 modes: the load controller, critical bit computing unit, and 3-to-8 decoder working during the weight loading to compute W and the associated 2 to 4-bit weights, whose overhead is only 1.6%. By effectively using the spare bit, the CASU increases the 36.3% of the SIM utilization. And for the third feature, it's the cyclically alternating the scheduling adder tree that reduces the energy for dynamic aligned accumulation. After completing the Mantissa multiplication in the SIM array, the shift alignment unit aligns the Mantissa multiplication results based on the exponent before performing the accumulation. In this process, due to the additional regime introduced by the POSIT to improve the dynamic range, the Mantissa width is typically very small. As a result, the aligned data often have no overlap, or only a few overlap bits. As shown in the histogram in this figure, For the POSIT-8 data format, 28.4 of the aligned methods have no overlap bits, and 62.6% of the methods have less than 2 overlapped bits. In particular, if A and B have no overlap bits, then A plus B is equal to A or B. Since the power of consumption of the OR logic is only 17% of the full adder, replacing the adder logic with OR logic is more energy efficient approach. We propose a cyclically alternating schedule approach to improve the replace efficiency of logic for adder by transforming the synchronous bit serial computation of A0 and A1 into asynchronous computation. As shown in this diagram, instead of computing A00 and A10 at cycle 1, we perform a 1-bit cyclically alternating for A00. Compared to the original A00, which should be here, the computation result of A01 is shifted 1 bit to the right, eliminating the original 1-bit overlap, which have potential to be here. As a result, we can still use the OR logic to replace the adder logic and obtain accurate computation results. For the next few cycles, the SIM array computes A0 I plus 1 and A1 I together. So the A1 has an index less than 1 compared to the A0, where the W0 times A0 plus 1 and W1 times A1 I have no overlap before if I is smaller than n. The overlap happens only in W0 times A0 plus W1 times AN, which uses 1 adder. As a result, the CASU saves n adders, instead of using n-1 OR logic with 1 adder. This approach increases the 36.4% no overlap ratio for a 31.1% power reduction. This slide shows the design of the architecture of CASU, which schedules the computation to increase the number of no overlapped conditions. Before performing the computation, the CASU fetches the exponent of 2 data and checks if there are no overlap bits, or there is. And if there are no overlap bits, the CASU directly replaces the add logic with OR logic. If there are overlap bits, the CASU performs a circular shift on one of the data to eliminate the overlap bits in the bit serial computation, allowing more addition operation to be replaced with OR logic and reducing the power consumption. As a result, the CASU saves 56.9% of the energy consumed by the adder tree during the accumulation. And next, I will show some measurement results. The proposed SIM macro is fabricated with the TSMC 28nm process. It has a total area of 1.41 square millimeters. The operating voltage ranges from 0.55 volt to 1.0 volt with a max operation frequency of 419 MHz and maximum power consumption of 338 milliwatts. It supports POSIT-8 and POSIT-16 data precision. And under POSIT-8.1, this kind of configuration, it achieves a maximum throughput of 3.86 teraops and maximum energy efficiency at 83.23 teraops per watt. For the ImageNet 1K classification on VLSI 18, the accuracy loss of this kind of POSIT data format is 0.12% compared with the baseline of FP16. This pie graph shows the power and area breakdown of the chip, and the PCSU and the CSU that we propose consumes slight power and area overhead. Compared with the direct regime processing and accumulation, the PCSU and the CSU reduce the regime processing and the adder tree energy by 40.3% and 56.9% respectively. The SIM array accounts for the largest power and area consumption, where the critical bit pre-compute and score facilitate the SIM array to perform dual-bit MAC operation in one cycle, improving the SIM utilization by 63%. And we compare our work with some, this table compares the measurement of three typical AI models, including training and inference. And for these models, the proposed SIM macro reduces the power consumption by an average of 7.93 times with less than 0.14% accuracy loss. The histogram on the right shows the breakdown energy efficiency contribution from each feature on ResNet 18 models. And compared to digital POSIT-based SIM improved the energy efficiency by 3.9 times. And the three features which we propose to handle the dynamic properties of POSIT provides additional energy efficiency gain by 1.12, 1.47, and 1.63 times respectively. And when compared with the state-of-the-art SIM macro, we can see that our work exploits the dynamic bit widths to adapt to varied data distributions. So it can achieve nearly the same accuracy as original FP16 or BF16. Also, the technique that we propose can effectively handle the dynamic regime processing, manage the storage and the line accumulation, facilitates our SIM macro to achieve significant improvements in throughput and energy efficiency. And I guess it's the time, so that's all for the presentation. Thanks for your attention.